Hi, I'm Arshita from JSS College. My topic is electronic spectra of octahedral and tetrahedral complexes. Introduction. To identify the ground state term and ground state symbols for atoms, splitting of terms in octahedral, tetrahedral complexes, Orgel diagram for D1 and D9 ions in octahedral and tetrahedral field. Introduction. Spectra due to the transition of electron from one energy level to another. Absorption spectra, it shows the particular wavelength of light absorbed, that is particular amount of energy required to promote an electron from one energy level to higher energy level. Emission spectra, it shows the energy emitted when the electron falls from the excited level to a lower level. The electronic transitions are high energy transition. In course of this transition, other smaller energy vibrational and rotational transfer also takes place, but the energy difference is small in vibrational and rotational transition. Therefore, it is difficult to resolve. The electronic transitions are high energy transition. They are governed by the selection rules. The transition which obey the selection rules are called as allowed transition, and the transition which disobey the selection rules are called forbidden transition. Allowed transition are quite common. The forbidden transition are not common. Allowed transition will have a big peak as shown here. Forbidden transition will have a very small peak. To identify the ground state term and ground state symbol for atoms, identify the microstate that has the highest value of S, find out the spin multiplicity 2s plus 1 and determine the maximum possible value of ML or L. Select the maximum value of J for more than half-filled subshell and minimum value of J for less than half-filled subshell. Example, P2 configuration will have only 2 electrons in the p orbital, so that is half plus half is equals to 1. S value will be 1. Spin multiplicity will have the formula 2s plus 1, that is equals to 3. L is equals to plus. The electrons are filled in a plus 1 and plus 0 state, so it is plus 1 and plus 0, that will be equals to 1. L equals to 1 means P state. J is equals to L plus S or L minus S. So 2, 1, 0 are the possibilities. Since P subshell is less than half filled, therefore ground state term symbol is 3p0. Terms for DN configuration, electronic configuration D1 and D9 will have 2D ground state term, 2D, D2 and D8 will have 3F, D3, D7 have 4F, D4, D6 has 5D, D5 will have 6S, D10 will have 1S. To identify the ground state term in octahedral complexes, sketch the energy levels T2G and EG, identify the spin multiplicity, determine the maximum possible value of ML or L. For high spin, there will be having a D5. Example of a high spin D5 system, the electrons are filled in the EG level first, and they are not paired up. They will be excited to they are filled in EG level. So S value is equals to half 5 times of that is equals to 5 by 2, and the spin multiplicity 2s plus 1, that will be equals to 6, and L value is equals to 2 plus 1 plus 0 minus is 1 minus 2, that is equals to 0. Therefore S state, L equals to 0 means it will be S state. Ground state term is 6s. For low spin d5, the electrons are not excited, they will fill in the lower energy only. So the electrons are paired up here. So plus of and minus of will be get cancelled. Only a single electron, that is half s is equals to half. And spin multiplicity 2s plus 1 equals to 2. L value will be equals to 6, and the ground state term is 2i. Splitting of terms in octahedral and tetrahedral complex. The wave function for SPDF states have the same symmetry as the wave functions for the corresponding sets of SPDF orbitals. An S orbital is spherically symmetrical and is not affected by an octahedral field, hence no splitting takes place in this case. Since all p orbitals lies on the axis, so there is no splitting of p orbitals in octahedral and tetrahedral fields, but energy of p orbitals is raised equally. A set of d orbitals is split into T2g and Eg in octahedral field and E and T2 in a tetrahedral field. Similarly, F term is split to three terms, T1g, T2g and A2g in octahedral field, or T1, T2 and A2 in tetrahedral field. Splitting of atomic states in octahedral and tetrahedral complexes. S term will split into A1G in octahedral and A1 in tetrahedral. The G term, G rate, will not be there in a tetrahedral field. So P will split into T1G and T1. D will have T2G and EG, T2 and E in tetrahedral. F will split into T1G, T2G, A2G in octahedral, T1, T2, A2 in tetrahedral. G will split into A1G, EG, T1G, T2G in octahedral, A1E, T1, T2 in tetrahedral. H will split into four terms, that is four terms, that is EG, T1G, another T1G and T2G in octahedral, E, T1, T1 and T2 in tetrahedral field. D1 and D9 ions, the ground state terms in 2D, and the orbital diagram is as shown below, as shown here. D1 system will have a 2D ground state term, and energy difference is as shown here, and the electronic transition will take place from T2G to EG in octahedral field and E to T2 in tetrahedral field. In D1 case, there is a single electron in the lower T2G level, while in the D9 case, there is a single hole in the upper EG level. Thus, the transition of a D1 case in the promotion of an electron from T2G to EG level, while in D9 ions, it is similar to consider as the transfer of a as the transfer of a hole from EG to T2G. Thus, the energy level diagram in D9 is the inverse of that of a D1 case. Example for D1 system and D9 system is shown here. D9 system will be splitted like this. The electronic transitions is taking place like from EG level to T2G in octahedral field and T to E in a tetrahedral field. It is shown here. Spectra of D4 and D6 ions for D4 system term symbols phi D and is splits into phi EG and phi T2G in octahedral field and phi T2 and phi E in tetrahedral field. D4 system is shown here. Electronic excitation from octahedral um, electronic excitation from EG to T2G in octahedral field. It is here and electronic transition takes place from T to E in a tetrahedral field. D4 system is one electron short to half field orbitals and it follows hole formation, hence the normal splitting is reversed. Here as D6 system shows normal splitting, energy will be in the y-axis and LF strength of octahedral field will be in the x-axis. Ligand field strength of a tetrahedral field in the x-axis. Electron transfer takes place from T2G to EG in octahedral field and E to T in tetrahedral field. Examples are shown here. D2 and D8 ions, the term arising for D2 configurations are 3F, 3P, 1S, 1D and 1G, out of which 3F is a ground state term, 3P term, both having the same multiplicity. Symbol is multiplicity. Symbol is used during the electronic transition from the ground state to excited state are allowed, while the electron from the ground state to another excited state such as S, G and D are spin forbidden. The orgel diagram corresponding to these allowed transitions for the D2 configuration with the octahedral field ligand can be shown in here. D2 system will have the splitting like this. 3F will splits into 3, that is A2, T1, A2, T2 and T1. 3P will having only one, that is T1. The electronic transition may take place from T1 to T2 or T1 to T1 and T1 to A2 in tetrahedral field, and here in the octahedral field the electronic transition can be from A to G to T2G or A to G to T1G or A to G to T1G. In the complexes with the D8 configuration in an octahedral field may be regarded as having two holes in the EG level, hence promotion of an electron from a lower T2 level to a EG level is similar to the transfer of a hole from EG to T2G. So this is inverse of a D2 case. D3 and D7 ions. The D3 ions has a 4F as ground state term. The other term of the same multiplicity is 4P. The 4F is splits into 4A to G, 4T2G, 4T1G, 4P. Is up splits remains as triplet degenerate. The three electronic transition can be same. D3 system is shown here in the below, and D7 system is shown here. 4F terms will be splits into 3 and P term will be having only one, that is T1. Example are shown here. Reference Coordination Chemistry Ajay Kumar. Book page number is 5.1 to 5.6. Thank you for everyone.